Hello everyone, and welcome to my talk on predicting length of stay with temporal pointwise convolutional networks. I'm Emma and I'm a final year PhD in Cambridge. So the topic of interest here is, can we predict patient length of stay in the hospital? And this is really important, especially at the moment when intensive care resources such as ventilators are really under strain. And this is really going to allow us to be able to plan ahead and really make it an efficient use of our resources. So the data that I'm using is actually an American data set containing over 200,000 ICU stays. From this, I extract the vital signs. So these are things that are constantly monitored, often in an intensive care setting. Then we also have lab results. So this could be things like coronavirus tests or other blood tests. Then we also have demographics, which are things that don't change over time, and then also diagnoses and medications. So this is just some example data for one patient. We can see that we have a lot of variability in the behavior of different variables here that I've got along the left. So the first three, these are quite rapidly updated, and these are all more of the vital sign kind of data. And the next three, these are lab results. So we can see that here we have long time gaps between samples. And it's very important that a machine learning model that we develop is going to be good at extracting information from both types of variable. So when we're designing the model, we really do take inspiration from how doctors think about problems. So if faced with, for example, a coronavirus patient, a doctor's going to want to know, how is the patient doing over time? Are they getting better? Are they getting worse? And also, are there ways of combining different parameters together to get more information? This is a bit easier to see with an example. So say that we have a coronavirus patient, they're experiencing some lung failure, they're having problems breathing. So the doctor's going to look at, how is the patient's blood oxygen doing? And is this getting worse or better over time? And they're also going to be interested in how much oxygen the patient's also breathing in, because it could just be that the oxygen is high purely because they're breathing in 100% oxygen, and it doesn't necessarily mean that they're ready to be discharged from the unit yet. So the thing that we use to extract trends over time is temporal convolution. So we can see here, if we organize our neurons in the network in this way, we can see from this output neuron in red, we can see all along the time series. And this is how we capture that temporal information. In order to extract inter-feature relationships, we have pointwise convolution, which instead of looking across time, just looks at one time point, and we extract all the information that we can across all the different variables. So this is what's going to be able to see what's going on with the patient's oxygen that they're breathing in and what's happening with their blood oxygen. We also add skip connections to the temporal convolution. So this allows you to skip certain parts of the network if it's found to be not useful. And we find that when we add this to the temporal convolution, instead of having to pass along these blue lines, we have an option of skipping part of the network and just going straight along these green lines. And that means that, say, for example, we have a lab result that doesn't really change much over time, or we haven't had an update for many, many hours, it might be fairly useless to look at what is the trend over the last few hours, because you probably won't see one. So this allows us to get more stable results from those, especially the lab results. So we arrange the temporal convolutions and pointwise in parallel, so that the model has the ability to do both kinds of processing. And yeah, so we find that like this model that we've designed is really going to hone in on those extracting trends and the relationships between features. And this is very different to the classic models that have been used more recently, like LSTM and Transformer. And we actually find that the skip connections allow the model to be able to choose how far back it's looking in time, which is very helpful for processing different kinds of features. So this is just to show the results that we've managed to get. The model on the left, I'm just showing a median model that will just always predict the median value no matter what the patient's data is. And we find that, okay, this gains a certain level of performance. I'm showing the mean absolute percentage error on the right and the mean squared logarithmic error on the left, which is the loss function that we use. Then the LSTM, channel-wise LSTM and Transformer, these are all baselines that other people have worked on, so this is related work. And then TPC on the right, this has managed to really slash the performance, and I really think that that's because we've thought quite deeply about the problem and what kind of processing we need to do to solve this task. So thank you to my funders and also my supervisor Pietro and collaborator at Microsoft, Stephanie Hyland. Thank you.